Friends, let's learn magnetic field along the axis of circular current carrying loop. Let us take a circular current carrying loop. This is a circular current carrying loop. Let the plane of the circular current loop is normal to the plane of the paper. This means that let the plane of the loop is normal to the plane of paper. This means that this board is the plane of paper. So this is the normal direction. We are taking the loop like this. So this is the loop. So perpendicular to the loop is this direction. So normal plane of the loop is normal to the plane of the loop is normal to the plane of paper. Now let us have a cut here so that from this side we enter the current. Let the current is anti-clockwise. This is two diagonally opposite side we are taking. This is the center of the loop and this is the axis of the loop. This is O point, this is A and this is B point. From O to A is radius A, let it be A. Let us take a tangent from A and tangent from B. Both meet at a point P. Here is the current element. You have here is a current element DL tangent. This is DL current element. So current element and this line R make angle theta 90 degree. Same here also, if you take the current element this side, so this make 90 degree. Now let us have a normal here at point P, so that it appear x and y axis. Now O to P is A, O to P is x. So R is A square plus x square under root. Now let us take a normal on the line AP. AP is extended, take a normal here. So this is a normal on this line. Similarly on the line BP, this is BP. Take a normal this side. So take a normal this side on the BP. This line indicate magnetic field dB. This is indicate magnetic field dB. dB by current element DL at A. In the same way, here we have a current element DL. So DL current element produces a magnetic field dB at point P, indicated by this. So dB can be resolved into two components. For that, this angle and this angle are same. Let the angle is phi. This phi is equal to this by geometry. Now dB can be resolved into two components, which is dB sin phi, dB cos phi. Again this dB can be resolved, which is dB cos phi, and here you have dB sin phi. From this diagram, it is clear that dB cos phi and dB cos phi cancel out, but dB sin phi added. So when you take 2 points, you have dB sin phi plus dB sin phi. So here you have infinite number of points in this loop. So you have to integrate to obtain magnetic field at point P. Let us see it. First, magnetic field at point P due to element DL at A. Magnetic field at point P due to current element IDL at A is dB is mu naught upon 4 pi IDL sin 90 degree upon R square. This is according to Biot-Savart's law. This is according to Biot-Savart's law. Now sin 90 is 1, so you have dB equals to mu naught 4 pi I dl upon R square. Now it is, as you have seen from this diagram, that dB cos phi cancel out and dB sin phi added up. So we have net magnetic field is equals to integration of dB sin phi. So net magnetic field at point P is net magnetic field at point P is, this is B. B equals to dB sine phi integration 0 to 2 pi a. This is the net magnetic field. Now you have to integrate this. So for integrating you require the value of dB, which is mu naught upon 4 pi I dl upon r square. And what is the value of sine phi? See in this diagram, in right triangle PAO, or you can say APO, sine phi is perpendicular by hypotenuse. So perpendicular is A and hypotenuse is R, A upon R. So here you have A upon R integration 0 to 2 pi. Take the constant term outside, which is mu naught upon 4 pi IA upon R cube integration 0 to 2 pi a dl. So you have mu naught upon 4 pi IA upon R cube. Here integration of dl is L, give a bracket here, write 0 to 2 pi a. So here you have mu naught upon 4 pi IA R cube into, here you have 2 pi a minus 0. So you can write this is this you can write mu naught upon 4 pi I a square, a into a square into 2 pi upon r cube. Let us cancel the common term, that is pi, and this 2 will cancel out, you get 2 here. So you get mu naught I a square upon 2r cube. What is the value of r? Value of r is a square plus x square under root. Put the value of r here. So when you put the value of r, you get b is equals to mu naught I a square upon 2, it is a square plus x square, half means root, and we have a cube here also, have a cube here. So this is mu naught I a square 2 a square plus x square 3 upon 2. This is the magnetic field at point P. Now let us have a special case. The special case is, if we want to find the magnetic field at point O, then at that situation x is equals to 0. So magnetic field at point O is obtained by putting x is equals to 0 in equation 1. This is equation 1. So put x is equals to 0. So what you have? A square into 3 by 2. So this 2 will cancel out. You have a cube here. So you have b is equals to mu naught I a square divided by 2a cube. So cancel this. So what you have? B equals to mu naught I upon 2a. This is, you have seen in the previous video that magnetic field at the center of the current loop is mu naught I upon 2a. If the loop have n number of turns, then multiply this with n and multiply this with n. Thus you have learned magnetic field on the axis of a current carrying loop. Do like, subscribe and share my channel. Thank you.